Dear students, welcome to the course Groundwater and Hydraulics, Module 2, Fundamentals of Groundwater Flow, Session number 8. I am Raja Anwar Hussain, Assistant Professor, Government Engineering College, Raichur. So in this session, we'll solve one problem and we'll cover it all on steady one-dimensional flow case with recharge. So here in this problem, at a certain point in an unconfined aquifer of 3 km square area, the water table was at an elevation of 102 meter. Due to natural recharge, in a wet season its level rose to 103.20 meter. A volume of 1.5 million meter cube of water then pumped out at the aquifer, causing the water table to reach a level of 101.20 meter. Assuming the water table in the entire aquifer to respond similar way, so estimate the specific yield of the aquifer and the volume of recharge during the wet season. So here given data, area 3 km square and SY specific yield we need to calculate. So then drop in water table is from 103.20 minus 101.20, and volume pumped out so here volume pumped out is equal to area into drop in water table into specific yield so volume pumped out is 1.5 into 10 to the power of 6 is equal to area drop in water table minus 101.20 and specific yield. So therefore specific yield, if you calculate, so here the specific yield is 0.25. So the second condition here, recharge volume is equal to 0.25 into 103.20, 102.00 into 3 into 10 to the power of 6. So the recharge volume so it is coming around 0.9 million meter cube. So here in steady one-dimensional flow case with recharge, steady unconfined flow with recharge, under steady state flow conditions, the groundwater level remains constant with time. Therefore, the groundwater level is a function of space only under steady state flow conditions. Steady groundwater flow occurs in an aquifer system when the rate of groundwater recharge is equal to the rate of groundwater discharge. So here, for steady one-dimensional unconfined flow subject to recharge or evapotranspiration, here the equation is h1 square bracket h1 square minus h2 square into x divided by L plus R divided by K into L minus x of x 0.5, where h of x is hydraulic head at a distance x from origin where x is the distance from the origin and capital L distance from the origin to the point where H2 is measured. H1 head at the origin and H2 head at the distance L and K mean hydraulic conductivity of the unconfined aquifer and capital R is the recharge rate. So this equation can be used to find the height of the water table anywhere between 2 points located L distance apart if the saturated thickness of the unconfined aquifer is known at the two endpoints, that is H1 and H2 are known. So in the absence of recharge, then the equation will be reduced to h of x so this equation is called Dupix's parabola. So by differentiating equation 1, minus k h dh by dx. So it can be shown that the discharge per unit width at any section x distance from the origin is q of x is given by, that is q of x is equal to k into h1 square minus h2 square divided by 2l minus r l by 2 minus x. If the water table is subject to recharge capital R, there may be water divide with a crest is in the water table known as groundwater divide. In this case, q of x will be 0 at the groundwater. So if d is the distance from origin to groundwater divide, then substituting q of x is equal to 0 and x is equal to d into equation. So then it will be d is equal to L by 2 minus k divided by R h1 square minus h2 square divided by 2L. Let us say this is equation 4, where all the variables have the same meaning as defined earlier. I hope you have understood all the sessions covered in this module 2.